Thanks for coming out to listen to me talk about Vulkan. I know it's the first day of Google I/O, and hopefully all the excitement of the first day hasn't died down for you yet. It's the last talk slot of the day, so I'm sure people may be anxious to get out of here and start partying. But we are here to talk about Vulkan, and it's exciting all on its own. It's one of my favorite topics to talk about, and I've recently been asked to maybe tone down the Vulkan talk a little bit. So it may be good for you or bad for you. Let's find out. So let's go ahead and jump in. So Vulkan, lots of rules and no mercy. I've used this line a little bit in all of my Vulkan talks because I feel it captures the general spirit of how people feel about Vulkan right now. And it's a bit of a joke because Vulkan does bring a lot of good things with it, but it does have a lot of complications that hopefully this talk will help address some of it. So a little bit of introduction before we continue. As you can probably see from the program, my name is Hai. I am a creative technology lead on Google's art copy and code team, and my role on that team is to explore different technologies to find out how we can leverage them for creative work. And some of the things that I explore are things like Vulkan. How do you leverage new graphics APIs for use in applications? And I started working with Vulkan about last December, a couple months before the February 16th launch. I implemented Cinder's Vulkan support on Android, Linux, and Windows, and then I subsequently ported all the demos to Vulkan. Cinder is a C++ creative coding framework. It runs on Android, iOS, Linux, Windows, OS X, and it's open source under the simplified BSD license. Currently, the primary render is OpenGL on the desktop and OpenGL OpenGL on mobile, and that's what it is now. Will it change in the future? Probably as Vulkan becomes more popular, with the exception of iOS and OS X, of course. And Cinder gets used in applications of all scales, anything from mobile to desktop to very large-scale installations that you might see in Times Square. Recently, Cinder has also been used in the clouds to generate content. Vulkan support became available in Cinder, as I mentioned earlier, on Vulkan's launch date. Since Cinder is a coding framework made to be used in very many general cases, the implementation is very much ongoing. So what this talk is not about, this is an advanced level talk, so it's not an introduction to Vulkan. It is not a tutorial on Vulkan, and it's not an in-depth examination on Vulkan. If you like a really good quick read on Vulkan, RenderDoc has a really nice Vulkan in 30 minutes document. And if you need to see some tutorials on Vulkan, we have some tutorials available on the GitHub repo. And if we were all to sit here and do an in-depth examination of Vulkan, it would probably take about a month. But feel free, if you have any questions specifically about any of the topics, just stop me afterwards or find me afterwards, and I'd love to talk about them. So what this talk is about, the bulk of this talk is how to get up and going in Vulkan in a kind of large way, not just writing sample code, but actually getting something to production. And so it assumes that you know about OpenGL ES, and assumes that you know a little bit about Vulkan or some other explicit graphics API like Metal or DirectX 12. And since Vulkan is definitely new, there are some sharp edges in Vulkan, and I try to point out the gotchas and why it's important to pay attention to things like device limits and the differences between desktop Vulkan and mobile Vulkan. And there's a short section on the things to consider if you're looking for performance in Vulkan. And again, these are kind of heavy topics, so if you find me say something that's weird and it's confusing, please find me afterwards, and I'll be more than happy to clarify them. All right, so to establish a baseline between OpenGL ES and Vulkan, so this question gets asked more than any other question when it comes to Vulkan. Is Vulkan faster than OpenGL/OpenGL ES? The short answer is yes, but not from a direct port. Vulkan is new, and if you want to leverage all the benefits of Vulkan, you have to change some of your code, if not a lot of your code, and definitely some of your thinking. Vulkan on mobile's feature set is comparable to that of OpenGL ES 3.1. However, it does go to include compute, geometry, and tessellation shader support. It is an explicit API. The developer is directly responsible or has direct control of almost every object in the rendering pipeline. The developer is also responsible for memory management. There are some new objects and concepts that do come with the API. There are also things that have similar names but function slightly differently. So one of the amazing features that Vulkan supports is validation layers. And if this is the first time you've heard of validation layers, they're essentially an API-level debugging error checking tool that lets you, that lets you figure out what's happening in the API. It's a very dramatic departure from GL get error. And the general rule of thumb for validation layers is to turn them on at the beginning of the project and leave them on until you shipped. The validation layers are cross-platform, which means the same validation code gets used on Android, Linux, and Windows. And one of the cool aspects of the validation is this. It's a function callback that you can supply to the validation layers that gets triggered every time a validation message gets triggered. And this is what the call signature looks like. And this is what a sample body looks like. As you can see, since it is, you can break it down into whatever granularity that you need based on the validation criteria. And if you're on a platform where you can't set breakpoints in the IDE, you can definitely set a breakpoint on any of these. And you can look in the call stack to see where the validation message was triggered. All right, so let's get a little bit deeper with Vulkan. Some friendly reminders before we start. And these are things that if you were getting a port from OpenGL ES to Vulkan, it's good to keep these in mind, even though they seem very trivial. The first thing is the coordinate systems. Vulkan's coordinate system is upper left origin. And this includes both rendering and texture coordinates. This one caught me off guard when I was first working with it. Everything I render appeared upside down and kind of backwards, and I thought I was doing something very wrong. Until I went and stared somebody down and asked them, why is it up or left? And there wasn't a clear answer, but it just is. And memory management basics. And in OpenGL, you didn't really have to handle a lot of allocations yourself, if any. In Vulkan, you have to kind of handle the majority of the allocations yourself. Buffers and images, definitely, and pools. Command pools are kind of handled for you, but descriptor pools are not. You still have to point out to Vulkan what you need. All right, so the first Vulkan topic, command buffers. So command buffers are one of those things in OpenGL that you hear a lot about, but you don't really have explicit control over. In Vulkan, that changes a lot. They are one of the primary things that you use to get pretty much anything done in Vulkan. And command buffers have to be allocated before their use. And command buffers are allocated from command pools. The command pools themselves must belong to a queue family, and we'll talk about queue families in just a minute. And when you're submitting command buffers have to be submitted to the same queue family as the command pool. And also, when you're submitting, you want to minimize the number of command buffers that you're using per frame. And when you hear this, don't try to use just one. If you try to use just one command buffer to do everything, you're going to end up starving the GPU. I also know that one through experience. It becomes quite difficult to try to fit everything to a single command buffer because you end up having to do a lot of code gymnastics. So in order to get to ensure the best performance, you're going to want to use multiple command buffers, but minimize them as much as possible. All right, so some sharp edges on command buffers. One of the terms that gets tossed around with Vulkan a lot is multi-threading. And while there is a portion of the API that is implicitly thread safe, there are parts of the API that are not implicitly thread safe. You can't record to the same command buffer from multiple threads, but it's perfectly fine for you to record to multiple command buffers on multiple threads. And you can do something where you can record multiple command buffers on multiple threads, and then take all those command buffers and kick them over to a single submission thread and submit all the command buffers from there. That's perfectly fine. But if you're going to do recording from multiple threads, make sure that each one of the threads has access to its own command pool. And directly related to command buffers is queues. Queues is, again, one of those things that you hear a lot about in OpenGL, but you don't quite have control of. In Vulkan, again, it's very different. And it's important to understand queues from pretty much their moment of creation. And queues, implicitly, they have to belong to a queue family. And you know which queue family they belong to through the queue family index. And there are a limited number of queues. And you can find out how many queues a queue family supports by looking at VK queue family properties queue count. And we'll get to the Q family properties in just a second. But if you find yourself in a configuration where you want to do both graphics and compute, you want to prefer the combined queues over queues that support singular operations. So if you're looking to do graphics and compute, look for a Q family that supports both. And the primary reason you want to do this is at the beginning, or just at the initial point of your port, it just makes things easier to coordinate. Because if you start using multiple queues from multiple queues, you will have to do synchronization, and that can be a little bit of a headache. When you're working with queues, it's important that if you need to order the queue operations, do it through synchronization primitives and avoid using VKQ wait idle in performance critical code. There are times when there are legitimate cases to use VKQ wait idle, but all the times there isn't, and through personal experience, it's caused a lot of weird bubbles in the pipeline and kind of stalls that I didn't expect. And some sharp edges in queues. So not all queues are universal. The queue family dictates what functionality each queue supports. An Android-specific notes on queue is that on Android, there's at least one queue that supports both graphics and compute. And you can present from any queue on Android. On the desktop, you kind of have to go looking around to see which queue supports presentation or not. And this almost goes without saying, but it's worth saying. You got to keep kind of precise counts on the queues. There are devices that only support one queue. So if a device supports one queue, it implicitly only has one queue family. So you want to check these properties before you start creating queues, because if you try to create more than one queue on a device that only supports one queue, you either get a hang or a crash. All right, pipelines, or pipeline state objects, as some people like to call them. Essentially, these are data structures that has properties that control pretty much everything that happens in the rendering process, and they're fixed function. So that means that once you compile them, you can't really change any of their properties. There's a caveat to that, since there are what are called dynamic properties, and the dynamic properties can be readjusted or can be adjusted via command buffer operations. And these include things like viewports, scissors, or blend constants. How many pipelines can you have? If you find yourself having hundreds or thousands of pipelines, that's actually perfectly fine. A typical application may have that many. And the reason, if you think about it for a moment, the different combinations of what you have in your rendering pipeline, in your rendering states, can easily create hundreds of permutations. But if you're getting to the point where it's over 10,000, you might want to figure out if you're having too many variations, or too much granularity in your variations. You can also cache pipelines, and the caching achieves two things. If you cache it at the driver level, it helps speed up the pipeline creation. You can also use a selection mechanism to where you can use a pre-made pipeline, and you can do this by looking at your pipeline properties and using a hashing function to select the pipeline. Excuse me. All right, so descriptor sets. And descriptor sets are one of my favorite areas in Vulkan, not because I have a fond affection for them, but I had to spend so much time with them. Descriptor sets are basically how the C++ side gives you a perspective into how the resources the shader will need. And there's a few things that may catch you off guard about descriptor sets, and we'll go over these things right now. The descriptor set binding numbers. So you can sparsely populate binding numbers on the descriptor sets, but keep the gaps small, because unused binding numbers still take up memory. There also is a max binding number. It's not obvious, but if you try to assign a binding number of like 32,000, most GPUs won't support it, and the validation will call it out, and they'll tell you that your binding number is too big. There's also a limit on how many descriptor sets you can have bound at one time. And this gets reported to you by max bound descriptor sets. And right now, if you try to bind more descriptor sets than your device supports, you'll just get a crash. And if the thing with descriptor sets is that you will need to update them once they're created, so the shader will know what resources you're looking at. So the general wisdom behind this is that you want to group descriptor sets by update frequency, and you only should update descriptor sets that have changed. Updating a descriptor set is fairly expensive. All right, some sharp edges on descriptor sets. Once you bind the descriptor sets, you can't do any updates to it until the next iteration of the command buffer, and then you should do it before binding. So here's the one really confusing thing that caught me off guard with binding descriptor sets. This function vkcmd bind descriptor sets, there's a parameter on there called first set. And it wasn't obvious from the spec what this meant, and so I thought it meant the index onto the p descriptor sets, which is another parameter. And to give you a better perspective, this is what it looks like. So at the bottom, you see the function signature. So this parameter actually refers to this field in your pipeline layout, and it's a little confusing because there's nothing that helps you figure this out. Somebody had to point this out to me. Essentially what this does is it aligns the descriptor set layout that you told the pipeline that you're going to use with the ones you're passing into the bind descriptor sets. So if you're running into a place where you're binding and you're getting a crash, or you're binding and getting like a fairly unexpected behavior, just make sure that these two parameters align. All right, frame buffers. So frame buffers in Vulkan are slightly different than they are in OpenGLES. You can think of frame buffers in Vulkan as basically loosely attachment pools. Essentially, they hold an array of VK image views. And the relationship between frame buffers and render passes are fairly, it's fairly strict. Subpasses and render passes refer to attachments by integer index. There's no ordering requirements. And the attachments in frame buffers must have the same width and height. In the general case, you still have to resolve any multi-sample attachments to single sample before you use them in textures. Not much different from ES. All right, so render passes, as mentioned before, subpasses inside of render passes refer to frame buffers, attachments via integer index. Subpass dependencies. So when you start working with Vulkan, you'll see a data structure called subpass dependencies. And from a high-level perspective, what this data structure does is that it builds a dependency graph that you pass into Vulkan to tell Vulkan the order in which you want the subpasses to be processed. If you don't do this, some GPUs will process the subpasses as they see fit, and this may not be the order that you want them to be processed in. So make sure that when you're working with subpasses, be really clear and explicit about which order you want subpass to be processed in if you're going to use an earlier subpass in the results of an earlier subpass in the next subpass. And additionally on subpasses, if you need to use let's say you're on subpass 3 and you want to use something from subpass 0, you need to preserve that attachment. If you don't preserve the attachments, what will happen is it'll get destroyed when the subpass completes. And further on the subpasses, if you have subpasses that have multi-sample output and you want them to get automatically resolved to single sample, you can pass in images into the subpass data structure that does this, and they'll get resolved right as the subpass ends. So here's a diagram that describes the relationship between subpasses and render and frame buffers. You can see on the right, the frame buffers are basically just a list, and the render pass is composed of multiple subpasses. And there's actually no need for you to share one depth pass. You can have as many depth passes as you want, assuming that it's within the device limits. All right. Okay, so these are the next two topics: image layouts and pipeline barriers. I wish there was more time to get in depth with these. They're actually really they're pretty complicated topics. So I'll try to go over them as best as I can. The behavior of image layouts, they vary depending on GPU. Some GPUs require very specific image layout transitions, others won't. The one thing that you should know is that all Vulkan petitions will accept VK image layout general for pretty much all operations. You will take a performance hit if you do that, though. So if you want to ensure best performance, it's best to assume that all GPUs require specific image layouts and set your code to handle it in that way. Transitions between image layouts are both implicit and explicit. The image layouts can be transitioned explicitly using pipeline barriers, and image layouts, they can also be transitioned implicitly by render passes. you basically, and how that happens is there's a field inside the subpasses that ask you, like, what do you want this to be once you're done. You can also use the validation layers to correct any image layout errors that you may have. The validation layers are very fond of screaming at you every time there's an image layout error. So it's a good tool to have around. All right, pipeline barriers, if you've used them in OpenGL, they can be a little bit terse. There's two things I feel like you should know. The first one is that while they do look complex, they become kind of second nature with some practice. The other thing is there's a restriction on pipeline barriers within render passes. And if you need to issue a render pass, or sorry, a pipeline barrier within a render pass, the subpass that you're going to issue the pipeline barrier in needs to have a dependency within itself. And you do that just by telling a subpass dependency the integer index of that subpass. And there's only two types of pipeline barriers that you can issue within a render pass, and that's VK image barrier. I'm sorry, VK memory barrier and VK image memory barrier. All right, so a little bit more advanced on the memory management. Since you're directly responsible for the allocation and usage of memory, just like regular old C, you need to do bounds checking. Make sure all your writes of buffers are bounds checked. If you write out of bounds, some drivers will let you get away with that, and what it does is it creates these incredibly difficult to track down bugs. It can create red herrings. It can create a situation where you overwrite something inside the vertex buffer, but it actually crashes when you try to do something with uniform buffer. So build some code around error checking to make sure that all your writes are in bounds. And flushing is something that's making its way back. After you do any host writes, make sure to flush. If you have command buffer operations that do a read, all the things that read depends on must be flushed before that read operation takes place. There is a slight caveat to the flushing. If you allocated memory with the VK memory property host coherent, you don't need a flush. All right, shaders. So SpearV is the official shading language of Vulkan, and it is a lower level language, so we're still using GSL for a while. It must be compiled either online or offline to SpearV using either shader-C or GL slang. The same shader code can be used on both desktop and mobile. There is a big change to uniforms. Obviously, you have to use uniform buffers, but you can't have standalone uniforms anymore. Uniforms have to be within block variables, and they have to be within interface blocks, and the layout of these interface blocks are governed by the STD140 rules. And if you ever worked with STD140, it can be a little bit complicated. In Cinder, we use spear to cross to actually extract the offsets and size information from the SpearV directly. And if that's something that interests you, come talk to me afterwards, because it saves us a lot of headache. The other thing is that you should, whoever is working on your team on bindings or between the shaders and descriptor sets, spend some time understanding how they relate with the descriptor sets and the shaders. There's obviously a natural relationship, but it's really easy to make an error in one and kind of ignore that it may create an error in the other, because you do have to keep them synchronized. All right, so performance considerations. So these are kind of self-evident things that we hopefully all hold to be true when we're talking about performance in graphics. Obviously, minimize hosted GPU transfers, especially on mobile, because that ends up taking a lot of power. Reduce round trips on any reads. That includes using compressed textures to speed things up. And in Vulkan, very specifically, try not to starve the GPU. Because when you starve the GPU, you can, the next round of you pushing data to the GPU can easily oversaturate it. And with respect to render loops, the best thing for you to do is to keep multiple frames in flight with Vulkan. I find this in Vulkan to actually be a lot easier to do than OpenGL. In OpenGL, at times I felt like I was at the mercy of the driver of what it was doing when I was trying to keep multiple frames in flight. With Vulkan, you can very explicitly do this because of how the nature of Vulkan. So if you have more than one frame in flight, say you have 2, then you obviously need to double buffer all your non-static resources. If you have 3, then you need to triple buffer your non-static resources, and so on and so forth. And this also includes things like your command buffer. And the command buffers are a good starting point if you need to figure out like what resources are backing that particular frame. So you can start building like a dependency graph from the command buffer back to the resource that you need. And so since you have multiple frames in flight, you'll probably need to handle the frame rate throttling yourself. This takes a little bit of work, and it requires both using the Vulkan sync primitives plus some CPU-side logic. And this is definitely an area where you do not want to use VKQ wait idle. I'm sorry, some of the Vulkan function names are really hard to say. And I know I'm screwing them up because they're a mouthful and they're really long, so I apologize for that. All right, so here's something that didn't exist in OpenGL, but I think it may be coming to OpenGL soon, is push constants. So if you're looking to do something really quick and there's not a whole lot of data that you need to pass between your code and the shader code, you can use push constants. And push constants, they don't require any buffers, they don't require any scripture setups. You can only push 120 bytes at a time. And the limitation on them is that you can only have one push constant for all shader stages per shader. And 120 bytes, you can fit about 2 4x4 matrices in there. So you kind of have to be a little bit clever of how you use them. And this sharp edge, the size and the offsets must be a multiple 4. It's not really a sharp edge. 4 is the default machine size for pretty much any GPU. So if your size and offset is not 4, something went wrong somewhere else horribly. But they are really quick and fast. And Cinder does have a sample of how to use this. And here's what they look like. It just looks like a uniform block, except where layout is, it has push constant. Excuse me. All right, so most projects will probably start on desktop and go to mobile. If you're not doing that, then you're really highly skilled. But for the rest of us, pretty much everything starts on desktop and then migrates to mobile. So Vulkan, the API is actually is crazy consistent. Cinder took 3 hours to port from the desktop to mobile. And the only thing that required changing was basically the WSI or Windows Systems Integration and the swap chain. And it pretty much ran. So I'm not saying that your code will take that short amount of time to port, but you can trust that the API is consistent. The only other area that's different is the extensions. So that's for the API. Now, the properties are a different story. So the properties for the features are very different from GPU to GPU. And those includes things like what image formats or buffer formats are host visible and what depth/stencil formats are supported. So don't assume that 2 devices that may be similar in capabilities that their Vulkan implementations are equal. I made that assumption, and I found that to be completely not true. So, if you must, write a little tool that queries the properties of the devices so it solidifies in your head what the devices are capable of. Since there's not a whole lot of Vulkan implementations right now, so you can kind of keep track of it that way. But it really helps. The other thing when you're porting is that have a strategy to find the best properties for that particular device. An example of this in Cinder is that we have a function called vkFindBest depth stencil format. And the reasoning for that is that on some of the devices, the best one was 32-bit float, while others only 16 and 24-bit integers were supported. Or at minimum, you can use properties that are known to work across all devices. All right. The other thing that you should be aware of is 3-channel format support is very limited, and this includes both image and buffer formats. So again, develop a tool that generates a device report on which formats are supported for the devices. And if you are relying on any data packing on your vertex or images, and you're using 3-channel formats right now, you may have to change the format that you're using. Which leads me to the next point is if you're also staging transfers between your source, your host data, and your GPU data, you may have to transform the data in the staging. An example of this is let's say your host format is RGB, on some devices, RGB8 isn't a visible host format. So you may have to transform that to RGBA, copy it to the Vulkan memory as RGBA, and then do the conversion inside of Vulkan. The other way to work around this is to do a direct copy from buffer to image, using VK-CND copy buffer to image. There's a caveat to that, I'll get in just a second, but this essentially does a bit-for-bit copy from the buffer to the image, so you can basically just read your image into the buffer and then dump it into the image itself. The depth stencil copies are very specific in their behavior, and there's a good portion of the spec that talks about that. Compressed textures. So you should know, I mean, we kind of all know mostly these days what formats are supported. The thing not to do is don't assume that if it's supported in OpenGL ES for the device that is supported in Vulkan, it may not be. One nice thing about Android in this regard is that all Android Vulkan implementations will support ETC2, and some of them will support ATSE as well. And just for completion, the desktop support is essentially just the BC formats. They may have slightly more complicated names. Excuse me for 1 second. Okay, so that's the last part of this, going from desktop to mobile. So again, not to harp on image layouts too much, but some GPUs will require very image layout transitions, and while others won't. It's just best to treat them as if they all do. And this is a really important point. I encourage you, if you have any questions about this, please come talk to me. I can't say certain things on stage, but I can give you specific details if you want to know more about this. So pay attention to the device limits. This almost goes without saying, but again, it catches people more often than not, is that most of the vendors will go above and beyond in certain areas of the device limits and not others. And some device vendors will just kind of do the minimum. And it's not because one vendor is better than the other, it's just the implementation, right? But don't assume that the same classes on devices or the same class of devices have similar functionality. They may not. And if you run into any errors, especially with device limits, you can use a validation layer to track them down. All right, so that's about 41 slides of me talking without showing you any pictures. And let me fix that right now. So these, I know the word games is used in the title of the talk, and I'm not going to show you game engine demos, but I would like to show you render demos if that's okay. And the point of these demos is to give more credence to the fact that Vulkan is up and running, and you can do some pretty amazing things with it already. And so hopefully these examples are visually enticing enough. Can we go to the demos, please? Okay, so this is a flocking simulation. It runs almost entirely on the GPU. It's a flock simulation of about I think about 4,000 fish, and essentially the fish simulation is run on the GPU, and there's a shark that comes in every now and then, and it basically causes the fish to disperse. The code for this is actually open source. It's a sample on Cinder. If you want to get it and mess with it, it's totally free. Whoops, stay awake. The original work was done by my friend Robert Hodgen, who was gracious enough to donate it as part of the Vulkan launch day efforts. And the next demo I want to show you is, it's also another demo by Robert. And essentially, this is, if you're familiar with NASA's capture of sunspots, this is what the images look like. So Robert wanted to create something that was a real-time version of the sunspots. So he just likes to create pretty pictures, but it turns out to be very beautiful. And the funny tidbit about this is that actually more than a few people have mistakenly thought this was the actual NASA capture. So this one, unfortunately, isn't open source, but if you would like the APK to either one of these, just come find me afterwards. I'll be more than happy to give it to you. Can we go back to the slides? Oh. All right. So to wrap things up, If you want to look at Cinder's Vulkan implementation, it's at github/cinder/cinder. We're on the Vulkan branch. If you want to connect with us about Vulkan, we really want to work with you to make Vulkan successful. Please visit this URL. Cool. Well, thank you, guys.